Welcome to part 2 of our Systems Engineering series on Amazon S3. For cloud engineers, storing files is only the first step. To build resilient, distributed systems, you must safely expose web endpoints, protect critical object states, and manage asynchronous global replication. S3 can natively host static websites by serving index.html as your default root page. This allows you to make HTML, CSS, and client-side media globally accessible over the internet without deploying any compute instances or load balancers. S3 inherently handles error routing for broken paths by directing invalid requests to an error.html file, providing a complete static server layer. This diagram illustrates the specific URL format S3 generates when you enable this feature. The syntax is dictated by the bucket's AWS region. Depending on the region, the structure uses either a dash or a dot immediately preceding the AWS region string, which then resolves to the standard Amazon AWS domain. If your application requires a custom domain, you can map these region-specific AWS endpoints to a fully qualified domain name by integrating Amazon Route 53. Bypassing compute instances to serve static assets creates a highly resilient presentation layer. Consequently, the security burden shifts entirely to strict bucket-level configurations. The most common architectural failure when first configuring static hosting occurs the moment a web client attempts to access the generated URL. The request hits a rigid barrier, returning a 403 forbidden error. To resolve this, you must explicitly disable S3 block public access at the bucket level, removing the first default deny boundary. Next, you must apply a bucket policy. This diagram outlines the dual-layer bypass flow. After passing through the open block public access gateway, the inbound request is validated by a JSON policy document, explicitly allowing the S3 getObject API action while keeping write operations firmly blocked. This specific API allowance is necessary to grant anonymous internet visitors read access to website assets, while ensuring your bucket remains secure from unauthorized modifications or malicious overwrites. Public exposure in S3 requires the intentional dismantling of two separate default deny security boundaries. To protect this newly exposed data from accidental deletes or buggy application code, you must implement S3 versioning. When a client overwrites an object, S3 doesn't destroy the block, it generates a sequentially numbered history. Legacy files stored before versioning get a null version ID, anchoring the stack. If suspended, new blocks directly overwrite the active version instead of stacking. Furthermore, any subsequent uploads while in this suspended state will strictly write over any files that carry a null version ID. With versioning active, S3 operates as a state-aware ledger, requiring systems engineers to explicitly track and manage metadata histories. This architecture changes deletion mechanics. Standard delete commands issued by an application to a versioned bucket do not physically purge data from the physical disk. When a standard delete API call strikes the ledger stack, S3 generates a placeholder block labeled 0-byte delete marker, capping the stack. This marker intercepts subsequent GET requests, bouncing them back with a 404 not found response, making the object appear deleted. Recovery is straightforward. Retrieve the version history and delete the delete marker, instantly re-exposing the underlying active version. A standard request contrasts with a hard deletion. If a user issues a delete request that explicitly specifies a unique version ID, S3 permanently purges that exact file from the physical disk. This maps out the multi-factor authentication delete boundary. MFA requires the caller to provide a hardware or virtual token code before authorizing a permanent deletion. This configuration prevents unauthorized users or compromised IAM credentials from executing destructive version ID deletions. 0-byte markers preserve application uptime during accidental code errors, while MFA Delete ensures that permanent data removal requires explicit multi-factor authorization. For global availability and cross-region disaster recovery, engineers rely on automated S3 replication policies. S3 requires strict administrative prerequisites to configure replication. Versioning must be enabled on both the source and destination buckets, and a cross-account IAM role must be provisioned with proper read and write permissions to transfer the files. You must also account for the core design requirement. S3 replication is strictly asynchronous. S3 copies modified blocks in the background to ensure the replication process does not introduce network write latency to your active client uploads. This map illustrates cross-region replication, or CRR. S3 utilizes the AWS backbone fiber ring to stream data globally between geographically separated regions, meeting strict compliance standards while lowering access latency for international users. When utilizing CRR, the IAM service role must explicitly cross an encryption boundary. It requires permission to decrypt KMS keys at the source bucket and immediately re-encrypt the packets with the destination KMS keys as they enter the new region. Same region replication, or SRR, maintains all data packets constrained entirely within a single geographical data center. SRR is commonly deployed for centralized log aggregation across multiple application buckets or for syncing isolated production and test environments without incurring the transit costs associated with wide area networks. Choosing between CRR and SRR forces cloud architects to evaluate data transport boundaries, balancing the requirement for global geographical redundancy against WAN transit costs and localized KMS overhead. Native S3 replication rules only apply to newly uploaded objects. The automated system strictly ignores any pre-existing bucket data uploaded prior to enabling the replication rule. To manage updates and deletes, S3 enforces strict isolation protocols across regions. By default, standard delete markers generated on the source bucket are not replicated to the destination bucket, preventing accidental enterprise-wide outages. This visual demonstrates the absolute isolation of a hard deletion. If a delete request specifies a unique version ID on the source bucket, S3 physically bars that request from crossing the replication link, protecting the replica from malicious permanent deletions. S3 also enforces one final highly critical replication limitation, the strict non-chaining boundary. This diagram maps out to the on-chaining rule. If bucket A replicates to bucket B, and bucket B has a separate rule to replicate to bucket C, the data originating in bucket A will strictly never propagate to bucket C. The engineering logic behind this physical limitation is clear. It actively prevents complex cascading replication loops and eliminates massive network write bloat across global corporate accounts. To push data past this non-chaining automation limit, copy pre-existing files, or reconcile failed syncs, administrators must deploy S3 batch replication to manually run bulk processing jobs across the global storage footprint. S3's strict isolation of delete actions and the hard block on replication chaining are intentional design choices engineered to prevent automated, enterprise-wide data corruption. This macro diagram illustrates the complete, unified S3 ecosystem we have constructed. The static web endpoint gateway securely feeds into the versioned logical ledger in the center, which then asynchronously streams data outward to isolated global backup buckets. Successfully engineering S3 requires deliberate security policies for static exposure, the active management of logical ledger states via null IDs and delete markers, and the strict enforcement of asynchronous replication boundaries. In Part 3, we will analyze the complete matrix of S3 storage classes, dissecting durability metrics, glacier retrieval mechanics, and intelligent tiering auto-scaling behaviors.